G'day dudes and dudettes, welcome back to Mathematics for another mechanics lesson. We're starting off with some more revision questions from the complex numbers topic. So if you remember this stuff, by all means hit pause and have a go. Otherwise, let's just dive into it. So for the first one, we are finding the minimum value of the absolute value of the argument of z given by the distance from z to negative 2i is equal to negative I squared. Okay, so the first thing we're going to do is write this in a bit more of a user-friendly fashion like this. So we're thinking of it as the distance from z to the point minus 2i, which is 2 down on the imaginary axis. And I squared is negative 1, so negative I squared is just equal to 1. So now we're reading this and we're interpreting it as a circle with a center at minus 2i and a radius of 1, which looks like this. Now we're finding the minimum value of the absolute value of arg z. So we're trying to find the smallest possible positive angle. Well, I guess it's always going to be positive because of the absolute value. But anyway, the smallest possible angle from 0 to a point on this circle somewhere. Okay, so to do this, we're going to put in a cheeky little tangent here. And this value right here, this angle here, theta, is going to be our smallest possible argument. Because if we go around the circle, the angle is going to get bigger from 0. So we want to find this theta right here. The way we're going to do that is we're going to use the fact that a tangent hits a circle at 90 degrees. Okay, and then the line from the contact point on the circle to the center of the circle is, like I said, always 90 degrees. So we can make a little right angle triangle here that allows us to do a cheeky bit of trigonometry. So we're going to say that inside this triangle, we've got 2 here and we've got 1 here because it's the radius of the circle. So we've got the 2, 1, root 3 triangle, which you should be familiar with from the advanced course. Which means the angle up here in the top is going to be 30 degrees, which means the angle out here in the rest of the quadrant is going to be 60 degrees. Okay, so 2, 1, root 3 triangle, angle right here is 30 degrees, so angle right here is 60, which is pi on 3 radians. Okay, for the next one, we're finding all solutions for n in this equation where n is a positive integer. Okay, cool. So first thing we're going to do is rewrite the expression using polar form and de Moivre's theorem. So writing 1 plus I in polar form looks like this. If you need some revision on going from Cartesian form to polar form, I do have videos on that already. And over here is our 1 minus I in polar form. Now raised to the power of n, using de Moivre's theorem, we're going to apply the power of the n to the root 2, and we're going to multiply the argument by n, which looks like this, all expanded out. And now for this, we can use the fact that because cosine is an even function, it doesn't care about the negative, and this is the same thing as cos of n pi on 4. And we can use the fact that because sine is an odd function, we can pull the negative out the front and have this as minus I sine n pi on 4. Expanding all that looks like this. That's convenient because the sine and the minus sign cancel out and leave us with 2 lots of root 2 to the n cos n pi on 4. Okay, now for this to be 0, obviously 2 root 2 to the n can't be 0, so the cos must be equal to 0. So we're trying to think about angles that go inside cosine and give us 0 as a result. So for that, we're thinking about 9 degrees. We're looking at 3 pi on 2, 5 pi on 2, and the pattern continues going up by 2 pi on the numerator each time. We're just going to tidy this up and solve for n. So let's multiply everything by 4 to get rid of the fractions. So we've got 2 pi, 6 pi, 10 pi. Dividing everything by pi, and we get 2, 6, 10, and so on and so forth. And so the pattern here is that we're starting with 2 and we're adding on 4 each time. So we can write our expression as 2 plus 4 times an integer, where k is an integer. Okay, so there is our solution for n that makes this whole thing equal to 0. Okay, on to today's lesson, which is all about forces and motion. So a bit of background knowledge on physics for today, and I'll try and give you the quick version because we're mainly focused on the equations in Extension 2 Maths rather than the theory. But a bit of theory does make setting up your equations a bit more logical, I would say. So starting off with my boy Isaac Newton and his 3 laws of motion, which he figured out about 400 or 500 years ago because he's pretty smart. First one is inertia, which says that an object will maintain its velocity unless acted on by another force. Okay, so if your velocity is changing, there must be some force acting on you to do this. So if you throw a tennis ball, it wants to do this, but it actually does this because of gravity and because of air resistance. So this is what the ball wants to do, but forces acting on the ball have other plans, and this is what actually happens. For the next one, we've got just the force equation. So force is equal to mass times acceleration. This is going to be the building block of a lot of our equations for the next few lessons. And so an example of a force is if you had a 1 kilogram tennis ball and you accelerated it by 1 meter per second, that acceleration would result in a force of 1 Newton. So that's how we define a Newton. It's 1 kilogram accelerated by 1 meter per second. And the last one is opposing forces. For every force, there is an equal and opposite reaction. So for example, when you throw a tennis ball on the ground, it wants to go through the floor because of gravity, but it doesn't. It bounces back up. And that's because the force that the ball hits the ground with, the ground exerts the exact same force back on the ball and forces it back up. Okay, so there's going to be a large part of our lesson on resisted motion, where every motion has something resisting against it and creates our force equations. But we'll get to that next time. All right, today we're going to be looking at force diagrams, which have been a feature of the last 2 years of the HSC, and I'm guessing will be the same thing this year. And these are the kind of things we have to think about. If we're pushing something, there's going to be a force acting against that force, such as friction. And if there's a weight force acting on anything on Earth because of gravity, obviously this box can't pass through the ground, which means there is what's called a normal force, an equal and opposite force acting in the other direction from the floor to the box. Okay. Yeah, more force diagrams. We'll look at some examples with these and you'll get a better idea. But yeah, if you've done a bit of physics or some engineering, you might already be familiar. If you're not, that's okay. We'll get there eventually. Okay, some examples of just creating force equations and picking the right variables and picking the right expression for acceleration, which ties into our last video. We've got a particle, mass m, on a straight line subject to a force F given by these equations. T time, displacement, velocity, blah, 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 blah. Initially at rest at the origin. There are conditions which we're going to use to find constants later on when we do some calculus. Okay, first question. Force is equal to 6 times time minus 4. Mass is 2. We want to find x when t equals 4. So first thing we're going to do is translate this from a force equation to an acceleration equation using the fact that force is equal to mass times acceleration. So for our first one, we're going to write the left-hand side as 2 times acceleration because the mass is 2. Now we're going to divide both sides by 2 and we have our acceleration equation. Because this question is asking us to find a relationship between x and t, and this one's already in terms of t, so it's a relatively easy example where we can just integrate to go from acceleration to velocity, and then integrate again to go from velocity to displacement. So writing our acceleration as the derivative of velocity with respect to time, integrating both sides with respect to time. On the left we get velocity, on the right we get the integral of 3t minus 2. That integrates to 3t squared on 2, take away 2t, and don't forget your constant. Let's figure out what the constant is using our conditions that initially, so when t equals 0, the particle is at rest, which means velocity is equal to 0. It's not moving. So we have 0 on the left, we've got 0 here, which leaves us with the constant must be 0 to make this equation make sense. So we can go back to our derivative, or our velocity, sorry. We can write the constant as 0, and now we're going to write the velocity as the derivative of displacement with respect to time, because we're going to integrate once more to go from velocity to displacement to answer the question. So integrating once more, we get 3t to the 3 over 6, take away 2t squared on 2, and another constant. Again, we'll use our conditions that initially when t equals 0, we're at the origin, so x is equal to 0. So this once again gives us that 0 equals 0 minus 0 plus constant, so the constant must be nothing, and we can just wipe it away. Simplifying our fractions, we get t cubed on 2, take away t squared. Question asked us to find the displacement when time is equal to 4, so we're going to substitute 4 into this expression and get our answer of 16 meters or something, I guess. There's no real units in the question, so we're just going to go with numbers. Okay, there's the first one. On to the next one. This time, force is equal to 2 times x plus 1. So instead of being in terms of t, it's in terms of x, which is a bit more challenging. Mass is 1.5. Find a relationship between velocity and displacement. Okay, so for this one, we're going to once again write our force as mass times acceleration, so 1.5 times acceleration. And then we're going to write our acceleration using our knowledge from the previous video as the derivative with respect to x of v squared on 2. Okay, after I multiply by 2 and divide by 3, of course. Let's get rid of the fraction on the left-hand side. Writing the acceleration as v squared on 2 as a derivative. Okay, when you're trying to find a link between velocity and displacement, and it's in terms of displacement, you've got to write your acceleration as the derivative of v squared on 2. Again, if you haven't watched my last video, that won't make sense, so please go back and catch up. Okay, we're going to integrate the right-hand side with respect to x, and so we're going to get 4x squared on 6 plus 2/3 x plus a constant. Let's figure out the constant. Our conditions are still the same. v is 0 when x is 0. So we get 0 equals 0 plus 0 plus constant. So once again, the constant is just nothing for this example. So there's our expression for velocity squared on 2. We're trying to find velocity when x equals 3. So let's just multiply everything by 2 to get velocity squared. And then we're going to sub in the value of x equal to 3 to get velocity squared. And then we'll take the square root of that and we'll take the positive value. So when we sub in 3, we get an answer of 16, which tells us that velocity must be equal to positive 4 because it says positive value. Okay, so when it's in terms of x, you got to use v squared on 2. On to question C. This time our force is in terms of the velocity. Okay, cool. So once again, starting off by writing force as mass, which is 0.25, times acceleration is equal to 1 over v plus 2. Okay, now because we're trying to find a link between t and v, that means we're going to write our acceleration as the derivative of velocity with respect to time. So typically, you want to write your derivative in terms of the two variables that you're trying to link. So you look at what the question's asking you to find, and that's how you figure out which of the three forms to write your acceleration in. So multiplying the 4 across and writing acceleration as dv on dt, we can't integrate both sides with respect to t, so we'll have to invert both fractions. We'll do a flipsy upside downsy as my class calls it. And now we'll take the integral of both sides with respect to v. So we get t is equal to, I'm just going to pull the quarter out the front of the integral and have v plus 2. Integrating this, we get the next step. Here we go. 1/4 of v squared on 2 plus 2v, and then we've still got the constant hanging out the side. Figuring out the constant, initially t equals 0, at rest v equals 0, so we end up with c equal to 0 once again, so we can just scrub that away. So there, if we expand out the 1/4, we get our expression for time in terms of velocity, which is all we need because now we can just find t when v equals 4 by subbing 4 into this. And we get a final answer equal to 4 seconds probably. Okay, and the last one for the warm-up. This time, next, here we go, cool. This time, once again, our force is in terms of velocity, so it's the same equation, except this time we aren't trying to find a relationship between v and t. We're trying to find a relationship between x and v. Okay, so starting off once again, writing force as mass, which is 0.5, times acceleration. And now we're going to multiply the 2 across, and because this time it's in terms of v, and we're trying to find a link between x and v, we're going to write our acceleration as v dv on dx. So we're using that third new form from last video. Okay, we're going to divide both sides by v, so that puts the v on the bottom of the fraction over the other side. And now we can't integrate both sides with respect to x, so just like last time, we're going to do a flipsy upside downsy before we do any integration. So upside down, we get v squared plus 2v on the top. On the bottom, we get 2. And now we can integrate both sides with respect to v, and it's going to get us our displacement in terms of our velocity. Okay, so integrating, pulling the half out the front, and now raising the powers and dividing by the new powers, adding your constant, which, spoiler alert, is going to be 0 again, because 0 equals 0 plus 0 plus 0. So no constant, we can expand out the half and get our expression for x in terms of velocity. To finalize the question, we're going to sub in v equals 3 to find the value of x, and we end up with a value of 9. There you go. So this is the kind of calculus we need to be working with for this lesson. We've got to be spotting which variables we're trying to find, writing acceleration in the right form, and don't forget that, of course, force is mass times acceleration. Let's do some more examples. Let's do that. Okay, example 2, this is from an old Victorian HSC paper. We've got a force of 10 newtons and a force of 8 newtons, both acting on a body, and they are 60 degrees apart. We want to find the magnitude of the resultant force, and we want to find its angle from the 10 Newton force. So if you've got 10 newtons this way and 8 newtons this way, the resulting force is going to be somewhere in the middle, and we want to find what the length of the line is and what the angle is from the 10 Newton line. So let's make some space. Okay, now to do this, if you have two forces acting on a body, you can kind of think of it as this force happens and then this force happens. So a better way of writing this diagram, or drawing this diagram I should say, could be to draw this 8 Newton vector up here. And so now our resultant force is going to be this vector plus this vector, which is going to be the resultant vector from here to here, like this. Okay, so our goal now is to find the length of this red line, and we're trying to find the angle inside this triangle. Which isn't too bad because we all passed year 10 and we know how to do trigonometry with non-right angle triangles, and that's really all you need to do this question from memory. So we're trying to find the magnitude of f, and we're trying to find the angle theta in here. So to do that, we need an angle inside this triangle. So let's think about what this angle up here would be, using the fact that this 8 Newton force is of course parallel to this 8 Newton force. If these are parallel, it means that these angles are what's called co-interior. So if this is a 60 degrees, it means up here must be a 120 degree. Now we can use the cosine rule because we have a side, angle, and side, and we can find the length of f, and then we can do some more fun trigonometry to find the the size of angle theta. Okay, so magnitude f squared using our cosine rule, we got c squared equals a squared plus b squared minus 2ab cos c, where c is 120. If we evaluate the right-hand side and take a square root, we get an approximate value of the magnitude of f being around 15.6 newtons. So finding the length of f using the cosine rule. Now we'll find the size of angle theta also using the cosine rule, because now that we have f, we have 3 sides in this triangle. We could have used the sine rule, but we can also use the cosine rule to find theta. So we've got cos theta equals a squared plus b squared minus c squared all over 2ab. Even though my answer here has been rounded a bit, I want to try and limit as much rounding as possible in my working out to make this answer more accurate. So whatever number you have in your calculator, try and use a fair few decimal points if you don't want your answer to be a little bit off. But for a question like this, which is multiple choice, that won't really matter too much. Okay, this fraction works out to be 0.89 bloody bloody blah. We'll take cos inverse or arc cos of that fraction, and we get a value of theta of about 26.3 degrees. I can't remember which one that was. I guess it was A. 15.6 newtons in length and 26.3 degrees to the 10 Newton force. Okay, cool beans. On to example 3. We've got, courtesy of the GOAT Howard Mathematics, we've got a 100 kilogram box sitting on a frictionless ramp, which is inclined at 30 degrees horizontal. The box is initially at rest. Find its velocity after 2 seconds. This question is more involved, and you really need to draw yourself a really cool diagram to be able to make heads or tails of this. This one's a little bit cramped, so I'm going to make my own over here. So we're going to split this 100 g force, because remember, forces are mass times acceleration. The box has a mass of 100 kilograms, and the, what am I saying? Mass times acceleration. Mass is 100, acceleration is g, where that represents the acceleration due to gravity, which is usually around 9.8 meters per second. Okay, we're going to split this, this weight force into 2 components, one going down the ramp and the other opposing the normal force going perpendicular to the ramp. So drawing a picture over here, we've got 30 degrees, we've got the weight force going down here, and there's our triangle that I tried to draw in here, but it was too small. Okay, we're splitting the 100 g force from gravity into 2 components, one going down the slope and one perpendicular to the slope. Okay, we're going to call this slope part B, and we'll call the perpendicular part A. Now, because this is 30 degrees right here, this is 90, which makes that 60, which makes that 30. So we need to use this 30 to figure out an angle inside this triangle so we can do some trigonometry. And because this A is perpendicular to the ramp, that's a 90-degree angle right there. So 30, 90, 60, 30, 90, 60. Okay, now this length here, this line here is the 100 g force from the weight, and now we're going to do a bit of trigonometry and say, okay, sine 30 is equal to opposite over hypotenuse, so it's b over 100 g's. We can multiply that across, and don't forget that sine 30 is equal to a half, so we rearrange this and we get b is equal to a half times 100 g, which is 50 g. Okay, so from this 100 g weight force that's going straight down towards the center of the earth, 50 g's of it is going down the slope. And that's what we care about because we're trying to find the velocity which is acting down the slope. Okay, so our force down the slope is equal to 50 g's, and now we can write force once again as mass times acceleration. Okay, the mass of the box is 100 grams. Why do I keep saying 100 grams? 100 kilograms. The acceleration we'll write as x double dot. Divide both sides by 100 and we get acceleration, which we're going to write as the derivative of velocity with respect to time, is equal to g over 2. Okay, the reason I'm writing acceleration as dv on dt is because the question is asking us to find a link between velocity and time. Find the velocity after 2 seconds. Okay, so integrating both sides, because the right hand side is just a constant, integrating both sides with respect to t, on the left we'll get v, and on the right we'll get gt on 2 plus a constant. Once again, information in the question to figure out the constant. Initially, the box is at rest. So when t equals 0, v equals 0, which gives us that c must also be equal to 0. All right, so here we have our equation for the velocity of the box down the slope. We're going to sub in time equal to 2 seconds, and we get 2g over 2. So the velocity after 2 seconds is equal to g, which is about, like I said, 9.8. Okay, cool. So yeah, pretty common style of question in Maths Extension 2 HSC is being able to split a vector into components so you can track its movements in individual paths, I guess, is a horrendous way of explaining it. Let's do another one and try and make more sense of it. This one is from another old Victorian HSC. Fairly challenging question. We've got a 5 kilogram and an 8 kilogram mass on a 8 kilogram mass is on a plane, a smooth plane, so no friction. They're connected by a string and the 5 kilogram weight is hanging down. The plane is a 30-degree incline. Okay, first question is asking us to draw on the diagram all the forces acting on both masses. So I already spoiled the weight force on both boxes heading down towards the Earth. So we've got mass times acceleration as our force going down, mass times acceleration, force going down. Okay, now because these two objects are connected by a string, there's a force acting on that string keeping them together, and that's called tension. So we're just going to write the tension force going up, connecting the two boxes. And now because this box wants to go through the plane and fall down to Earth, but it can't because there's a surface here, there must be a reactive force or a normal force acting perpendicular to the plane. So we've got gravity, we've got tension, and we've got a reactive force off the surface of the plane. Okay, now for part 2, if we go back to that because I forgot what it is. Back we go. Okay, find the magnitude in meters per second and state the direction of the acceleration of the 8 kilogram mass. Okay, so we're trying to find which way and how much the 8 kilogram mass is accelerating, whether it's going up the slope or if it's going down the slope. Okay, so once again, this question gets a bit easier if we draw a better diagram. So here's a better diagram of, we've got the 8g force. I'm just going to put like here and make a triangle as shown over here. So we've got 8g's going down, we've got 5g's going up the plane because the weight of the 5g box is pulling down. Tension is connecting them, so this tension force is equal to the weight force, which is 5g's. Okay, so because the 5 kilogram box is being weighed down with a force of 5g's, and because they're connected, that force is pulling the 8 kilogram mass up the slope. That's why there's a 5g right there. R is the reactive force once again that's preventing the box from falling through the surface of the, whatever this thing is, a ramp. Okay, now what we're going to do is we're going to say cos 60 is equal to b over 8g. In this triangle here, cos 60 is equal to adjacent over hypotenuse. Again, the reason we're trying to do this is because we're trying to find the magnitude of this force, b, which is acting down the slope. Okay, so cos 60 is b over 8g. Cos 60 is conveniently equal to a half, so this rearranges to 8g times 0.5, which is 4g. Okay, so if we have our net forces, we have a force of 4g going down the plane. That's the force of b, which we just calculated with trigonometry. But there's a force of 5g pulling us up the plane because of the weight of this box right here. So our net force, we have 5g's going up and we have 4g's going down. So our resulting force is positive 1g going up the plane. Okay, so there's our force. Let's write our force equation. Force is equal to mass times acceleration. This is where things get a little tricky because the mass of this thing is a little bit trickier because you have to keep in mind, this is 8 kilograms and this is 5 kilograms, but because they are connected by a string, you have to kind of consider them as one object with a mass of 13 kilograms. So the right-hand side is actually going to be, so left-hand side is the force, which is g. The right-hand side is mass times acceleration. Mass is equal to 13 because of the two blocks combined, and acceleration is, of course, a. Now we're going to write acceleration equals g over 13, and is that the end of the question? Yeah, it was. There you go, acceleration. So we've got the direction is up the plane, and the magnitude is g over 13. The question asks for the direction and magnitude of the acceleration of the two boxes. All right, cool. I was a bit scuffed, but you get what you pay for on mathematics. Okay, example 5 from the 2020 HSC exam. We've got a 50 kilogram box initially at rest, pulled along the ground by this 200 Newton force at a 30-degree angle. So someone's like dragging this box with this chain at this angle with this force. We've got a resistive force because the box is moving this way, and we've got some friction. So opposing the motion is a resistive force of 0.3 R, and that R is equal to the reactive force of the weight on the surface. Okay, so 50 gram, why do I keep doing that? 50G force acting down the box due to gravity, and a resistive force acting back up because it doesn't pass through the ground, because that's not how ground works. Okay, part I, by resolving forces vertically, show that R is equal to 400. Okay, cool. So what we'll do is we're going to make a little triangle out of the 200 and the 30 degrees here, and we can split this force, this 200, into a vertical and a horizontal component. The vertical part will consider these two, and the horizontal part will consider the 0.3R. So a bit of trigonometry, we can figure out that the adjacent side is 200, so it's hypotenuse times cos 30, and the opposite side is always going to be hypotenuse times sine 30. So that's a little shortcut you can take when you're making your triangles. If you've got an angle and a hypotenuse, the adjacent side is hypotenuse cos angle, and the opposite side is hypotenuse sine angle. Okay, so we get cos 30 is root 3 on 2, so this works out to be 100 root 3, and sine 30 is a half, so this works out to be 100. Okay, so for our vertical forces, we've got the resistive force of R going up, and also we have, out of our component from the 200, we have a component of 100 going up, as we can see here. So vertically, we've got R and 100 going up, and down we have the gravity force, which is 50G. So what are we trying to show? We're trying to show R is equal to 400, so we'll just add the 100 across to, we'll use the fact that in this question, they've approximated gravity to be 10 meters per second, so 50 times G is 500. Take away 100 from both sides and you get the required target of R equal to 400. So this resistive reaction force moving up off the ground is equal to 400. Part 2, show that the net horizontal force is approximately 53.2 newtons. So like I said, we've got two things happening horizontally. We've got the horizontal component of the 200 newtons just here, and we have the resistive friction force of 0.3 R, and we just figured out in part I that R is equal to 400, so we can figure out this number pretty quickly. So horizontally, we've got the 100 root 3 going in the right direction, so we're going to take this as positive, and in the negative direction, we've got 0.3 R as our resistive force. R is 400, so our net result for the horizontal direction is 100 root 3 minus 120 in this direction. And is that the answer? Yeah, about 53.2 newtons as an approximation, which is the target, so we know we did it right. Okay, part 3, find the velocity of the box after the first 3 seconds. So the box is not moving up or down, the box is moving horizontally. So to find the velocity, we're looking at the horizontal component, which is right here. So we're going to make a force equation. We've got force is equal to ma. We just figured out the force from part 2. We're just going to use the exact value rather than the approximation because we're not engineers, we're mathematicians. On the right hand side, we've got the mass of the box is 50 and we've got the acceleration is equal to a. Okay, so dividing both sides by 50, and because we're trying to link velocity and time, we are going to write our acceleration as the derivative of velocity with respect to time. This is just a constant, and we can integrate both sides with respect to t, and we get v is equal to this number times t plus a constant. If we use our initial conditions of initially being at rest, we figure out that the constant is 0, so we could have just forgotten about it and got away with it. All right, answering the question by subbing in the value of t equal to 3 seconds, we get velocity equals this times 3, which works out to be approximately 3.192 meters per second. Okay, so as long as you are comfortable with splitting this 200 Newton force into two components, this is a relatively easy 6 marks from an HSC paper. So it's the first step of being able to handle this vector, makes this whole question very, very doable in my opinion. If I can do it, I'm not a physicist, so you guys can. Okay, that's it for today's video. Hopefully that added some value to your life. Thank you for watching, and I'll hopefully see you in the next mechanics video, which will be on resisted motion. That's going to be so tough. All right, cool. Thank you for watching. See you next time.